All right, let's get into it. Today, we're going on a pretty cool journey. We're going to follow a single line of code from the moment it's written by a human to the moment it actually makes a computer do something. This is the story of how our ideas get turned into machine instructions, and it's the process that powers basically every piece of software you've ever used.
You know, it really does feel like magic, right? You click an icon, you press a key, and bam, something happens on screen. But what's really going on under the hood? Well, it's not magic at all. It's actually a super precise, logical set of steps. And we're going to unpack that entire process, starting right from the very beginning, the human-readable blueprint. So yeah, every single app, every game, your entire operating system, it all starts out as just text, a blueprint, a set of instructions that a person, a developer, can actually write and read. And for our example today, we're going to use one of the most foundational languages of all time, C. Okay, so check this out. This is what a tiny piece of that blueprint looks like in C. Now, don't get hung up on the weird brackets or the semicolon. The big idea here is this is just text. You and I can read it. It's basically telling the computer, hey, print the phrase, hello world, on the screen. That's it. To really get how this works, though, we need to zoom in on two of its fundamental building blocks. First off, that main part is what we call a function. And honestly, the best way to think about a function is like a recipe in a cookbook. It's a named block of instructions designed to do one specific job. A big, complicated application is really just a ton of these little recipes all working together to get something bigger done.
The other key pieces here are keywords. Words like int, if, or return. Think of these as the fundamental verbs of the C language. They're reserved, which means they have a special, built-in meaning that we can't change. They make up the core vocabulary that we have to use to write our instructions.
Okay, so we've got our blueprint, written in something that looks a little bit like English. But here's the problem. The computer's brain, its processor, has no clue what printf means. It speaks a completely different language, the language of ones and zeros. So our human-readable blueprint has to run through what I like to call a translation gauntlet to turn it into something the machine can finally execute. And this whole translation process basically breaks down into three key stages. First, a preprocessor comes in to tidy things up. Then, the compiler does the really heavy lifting, the actual translation work. And finally, a linker comes in and assembles all the different pieces into a single runnable program. Let's start with that first step, pre-processing. You can think of the preprocessor as a super helpful but kind of simple assistant. Look at the code on the left. We've basically told it, hey, whenever you see the letters PI, I want you to replace them with the number 3.14159. And that's exactly what it does. On the right, you see the result. It just went through and did a simple find and replace. It's a small step, but it gets our code all prepped and ready for the main event. All right, now for the star of the show, the compiler. This thing is the master translator. Its entire job is to take our cleaned up C code, which, remember, is still just text, and convert it into object code. That's the machine-level language, the ones and zeros, that the computer's processor can actually understand. This is, without a doubt, the most critical step in the entire journey. But we're not quite done. Our Hello World program used that printf function, right? Well, we didn't write the code for printf ourselves. It lives in a standard library of tools that comes with the C language. This is where the linker comes in. It acts like a project manager. It takes our compiled code, finds the precompiled code for printf, and links them together, bundling everything into one single complete executable file. And there we have it. Our code has survived the gauntlet. It's been preprocessed, compiled, and linked. It's not just a text file anymore, it's a real executable program. So, the moment of truth arrives. What actually happens when we run it? Well, when you double-click that file, your computer's operating system loads it into memory, into RAM. The processor then starts reading and executing those machine code instructions we created, one by one. And the computer's memory, it becomes the program's temporary workspace, like a scratch pad for storing values and keeping track of its progress as it works through our recipe. Now, there's a very specific reason we've been using C as our example this whole time. C has, well, a secret weapon, a feature that makes it unbelievably powerful and explains why it's still the foundation for so much of our modern technology. And that weapon is direct control over the computer's memory. C gets this control by using a concept called a pointer. So think of your computer's memory like a giant street of houses, and every single house has a unique address. Most variables are like storing things inside those houses. A pointer is different. It doesn't store a thing. It stores the address of a house.
It literally points to a specific location in memory.
And I know that might sound a little technical, but it is everything. This is C's superpower. Having that direct address gives the programmer fine-grained, totally unfiltered control over the computer's hardware. You can go directly to any memory location, see what's there, and change it if you need to. And this is precisely why that control matters so much. It's what allows developers to build extremely high-performance software. We're talking about the guts of operating systems, the device drivers that make your hardware work, and the graphics engines in demanding video games. By manipulating memory directly, programmers can cut out the middleman and squeeze every last drop of speed out of the machine.
So this brings us to the big picture. C was created decades ago. It's an old language. So why does it still form the very bedrock of modern computing? Well, it really all comes down to a fundamental trade-off. When you compare C to more modern languages, it becomes pretty clear. Many newer languages add safety features and layers of abstraction, which are awesome for building web apps or data science tools. But those features come at a cost. They add overhead and they reduce speed. C makes a different deal. It gives the programmer maximum power and performance, but in return, it demands the responsibility of managing all that memory by hand. And that's why C is the unseen foundation of your digital life. The operating system you're using right now, largely built with C. The fast-paced action in your favorite video game, it relies on C or its close cousin C++ for that direct hardware control. Even the tiny bits of software running on your TV, your router, or inside your car are often C, because it's efficient, it's fast, and it is as close to the metal as you can get. So, from a simple text file to a powerful application, that's the journey. It's a story of translation and control, and it leaves us with a really fascinating question to think about. As our programming languages become more abstract and easier for us to use, what are the trade-offs? What do we gain in simplicity? And what, if anything, do we lose by stepping away from that direct, intimate connection to the machine?